Now let's think about the graph of the sine function. So the function, first of all, we look at sine as a function of the variable t, sine of t. So this function depends on t. And if we want to see the behavior of the function, we hope to draw it. So, but let's look at the function at different values of t. Is the function defined for any real number t? Let's first of all look at this angle in radians. And we know when we use a unit circle, the unit circle, that means circle of radius 1 here. So we can have the convenience that to correspond the xy coordinate with cosine sine values. So here, the unit circle, and you have the same value because on the unit circle, the intercepted arc by the angle of t readings will have the same value. So that means that if the angle is in t readings, the intercepted arc will be t. So t is just a number. We can consider t as any real number. So we define our, let's look for the sine value. Sine value is the same as the y coordinate of the point on the terminal side of the angle, the less on the unit circle. So we just simply make good use of the unit circle. That is, as long as my point P is on the unit circle and the y coordinate of P will be the sine value of T. So in order to know whether the sine T exists for all T, let's just imagine, okay, let's see if when T is 0, right? When this T is 0, that is its terminal side and initial side will overlap, and the y coordinate is 0. Yeah, so when t is bigger, so let's imagine another t. So just increase. This is a different t. So then the y coordinate of this t, because the point is here, right? So the y coordinate will be the sine value. You see, it's positive. So that's the sine t. It is positive. And just to examine the y coordinate of point P. Okay, suppose you have another t. So I just use the pink color to show for different values of t, what is the what happens to the sine t, right? So sine t will be this value, this y coordinate of P. And we see that when T is getting bigger in the first quadrant, you see when T from here to here, and it's easy to see the larger T has the larger y value until here. So when the terminal side of t is on the y-axis, on the positive y-axis, then that t is half of pi. For this t is half of pi, the y reaches the largest possible value, right? It is 1. Because keep in mind, this xy coordinates, right, can be at between -1 and 1 because it's the point P is moving along the unit circle. So the y coordinate is at most 1. So that's the largest possible value for the y coordinate, which is the sine t. So as t changes from 0 to increase to half of pi, we notice the y coordinate of the point P increases, right? Positive from 0. So the sine t, as t increases from 0 to half of pi, the sine t, just pay attention to the y coordinates. Coordinate. What happens is increasing from 0 to 1. So let's just pick a few special angles. So if I pick, for example, we know already the some special angle. So let me give the table. We just look at the first quadrant from 0 to 1. We can even pick a few special points. That is okay. Okay, I'm going to show the few points. Okay, from 0 here when t is 0 and the sine value is 0. When t is pi over 6, the sine is half. When t is pi over 3, which is in degrees, will be 60 degrees, right? It's half of square root of 3. When t is half of pi, you get 1. So we can actually, because we know the exact values of the sine t for some special angles already, so we can just show them here on the points. So you notice an increasing pattern. So that is we plot, you see, for a given t value, you get the sine t. So 0, 0, that's the point here. And another t value, so if I have another t value, suppose it's pi over 6, and then we get a sine t value, which is half. So that's another ordered pair, which we show on this plot. So the horizontal axis is t, and this vertical axis shows the function value at the t. So next point is pi over 3. So pi over 3. And then what is the sine value at pi over 3. Then we get another point, and then at half of pi, and we get 1. Yeah, so each time we have this ordered pair, then we can get a point of the function. So far in the first quadrant, we have finished, we get at least 4 points, right? Very special points because they are special, yeah, locations of t, and then we get exact value of sine of t. And then we can get a sketch of the curve, which is this portion. Yeah, so we get for the first quadrant. And then if we continue to look at the behavior of sine, but if we continue to increase by pi over 6, right? Pi over 6. So you can create more points. So just from pi over 2, you add another, you see, increase pi over 6, you add another pi over 6, you get another pi over 6. So that is the list of points. I want to increase the t value by another pi over 6, and then by another pi over 6. And then I will get pi. And then just keep increasing each time we increase the t, the value of t by pi over 6 until I get 2 pi, which returns to the same position as start with. That's the 0, because 2 pi is a complete rotation. So the terminal side will overlap with the initial side again. So it has the same terminal side as the t equals 0. So that finishes one complete cycle. So let's, because they're all special angles, so we can really see the corresponding, the sine value of t, of each corresponding t. Recall that you can use the reference angle, and because the reference angle will be either pi over 6 or pi over 3 or some quadrantal angles. So then you can find the sine value very easily. So let's go back to that unit circle. We look at something we can predict. So suppose we have so I want to increase the figure so you can see better. So I just increase. Okay, now assume we have this angle T. Now we focus on the second quadrant. Focus on second quadrant, that is the terminal side will be here. So if the P continue to increase, now go be the terminal side of P will be in the second quadrant. So we know the x coordinate, right? X and y coordinate of the point will be cosine t and sine t respectively. So we can look at this same point, x, y, or cosine t, sine t. So we can view it that way. But that is to emphasize that when we are now focusing on the sine value of a t. So this, what happens is that when t increases, let's pick two separate locations. So one is the pink, one is red. So let's assume I have another point P corresponds a different T in the second quadrant. So here, this is another T, right? With the, oh, they share the initial side because they are both in the standard position. So here, so we're looking at in the second quadrant. So that is, I'm looking at a T that is bigger than half of pi, but less than pi. So for the t's in this range, so let's look at the sine t. So sine t for this y, the first y coordinate I drop, we can see the y coordinate. This is the sine t for the pink t, right? The angle. Just look at the y coordinate. And for the larger t, and the sine t will be this y coordinate. Because this point t, the x is the cosine t, y is the sine t. So just interpret with this picture, we can see what happens to the sine t. So when t in the second quadrant, the larger the t, the smaller the sine t. So that is sine t decreases. It decreases from 1 to 0. Because if we include half of pi, at half of pi, the sine t is 1. At pi, the sine t will decrease to 0. So yes, you can always draw that the case when at pi, then the point P will be here, and the y coordinate of P will be 0. So that's our sine t. So in the second quadrant, we notice the sine function is decreasing. It will decrease from 1 to 0. So we can look at the plot. Okay, so this plot of the sine function in the second quadrant, do we see that? That is when t is from half of pi to pi, the sine t will decrease from 1 to 0. So that's, so far we got the sine curve in the first, from t, for t, from 0 to pi. So we see increase to 1 and then decrease to 0. So when t is in this, we see the picture of the sine of t. Now later, we want to check, actually we got already the points, right? At each t, the sine of t are plotted. And you can see in the third quadrant, the sine t function will be decreasing, will continue to decrease until it reaches -1. And then afterwards, it will increase to 0. So we're going to look at when t is in the third quadrant, that is when t from pi to 3 pi over 2, and also when t in the fourth quadrant, yeah, from 3 pi over 2 to 2 pi, and see whether they agree with those data points. Just from a different perspective, we try to understand the behavior of a sine curve. So suppose you pick another t, which is in the third quadrant. This is a t. Here, initial side to the terminal side. That's our t. So for this t, what is the sine t? Let's try to visualize. The sine t will be negative, right? So here is the point P, because it's x coordinate is cosine t, y coordinate is sine t. Just I keep reminding you that. So the y coordinate of P here, this line, you see it is negative. Okay, that is our sine t for this t. And let's draw another t, suppose a larger t. So I go to this spot. That's another t. So we indicate from the standard position this. That's the t, right? For this t, this right t, and its corresponding sine value, which is the y coordinate of this point P. So let's just see that sine t. And we see that the previous t has a sine t which is less negative than the larger t. So you see between the in red and the t in black, and so when t is increased, right, the red t is larger, because we're looking at two different t values in this range from pi, bigger than pi, but less than or equal to 3 pi over 2. So we're looking at the two positive t values in this range. And then the second t, I mean the right t, certainly is bigger. What happens to the sine t? The sine t is more negative. So that we notice the sine t so as t increases from pi to 3 pi over 2, the sine t decreases and more negative. So decrease from 0 to -1. So as we can see, if you have this pi, and we know the sine t is 0. At pi, the sine t is just 0. At pi over 3, the sine t will be You see at this point. So if you have a angle that is all the way to this pi over 3, then the sine t will be -1. So it is decreasing. It is in the for the third quadrant, n and t in this range, the sine of t always smaller for the larger t. Yeah, you see negative and more negative, right, when t increases, and until you reach the -1. Yeah. So that verifies the picture we saw earlier. And for the fourth quadrant, we can still see that for n in, just to draw an angle, just to draw a t for any real number t. So this time we're looking at a certain t in this range, in the fourth quadrant. That is its terminal side fall in the fourth quadrant. And the t is still, yeah, within it's a positive less than equal to 2 pi, but bigger than 3 pi over 2. So we can see when this p moves in this along the unit cycle, then what happens is, okay, the y coordinate, you can predict what happens to this y coordinate, which is sine t. Okay, just imagine what happens to sine t when this t increases, right? When t increases in this range, the larger t will correspond to always a negative value of sine t. So sine t is certainly negative, but the larger t will correspond to a less negative. So let's think of another t, so just larger. So get this. And this is sine t here, sine t. So we just draw another, and for another t in this range, but larger, and its sine t is negative, but less negative. So that means the sine t is increasing from what? In this range of t, that means let's include 3 pi over 2. At 3 pi over 2, the sine t is -1. And then it's becoming less and less negative, increase to 0. Because at 2 pi, you will have the same terminal side as like a 0 degree. So 0 radians. And then you have a 0 sine value. So that verifies actually from a different perspective, help you understand the picture. So that's why we get a sine curve from 0 to 2 pi. And the sine function has a function value always is at most 1, at least a -1. Just imagine that unit circle, so that will help you understand the sine, the basic sine function, right? For whatever input value t, the sine value will be at most 1. So the maximum happens at pi over 2 and at least the negative 1. So the negative 1 happens at 3 pi over 2. So if we only look at a complete cycle of the sine curve, but remember the t can continue to increase. That means after you get one complete rotation, you can still increase t, make the t value larger than 2t. So yeah, you can have values bigger than 2t, etc. You can make it as large as possible, but the behavior will repeat because we know that if we have reached the 2 pi and then we add another pi over 3 or pi over 6, and we know that this has the same sine value as pi over 3, right? So if we do the sine of this angle, we will have same sine value of pi over 3. So that shows that 2 pi is such a positive number that for any t, it doesn't have to be pi over 3. For any t, if we add a 2 pi, that means you add a complete rotation, then the terminal side of this angle will be the same as terminal side of t. So let's write a t here. So we think 2 pi plus t and t, they share the same terminal side. They have the same terminal side, therefore they have the same sine value. And this is an identity. That means it is always true for whatever t. And the two angles, they differ by a complete rotation, right? It is always true. So 2 pi is such a positive number that it is actually smallest positive number that make the sine function curve repeat itself. So we can remember that 2 pi is called a period of the sine function. So the graph of the sine function is, since we draw one period of the sine function, you see from 0 to 2 pi, then you can imagine that the next period will be the same because okay, so let's so let's go ahead, look at two periods of the sine function. So once we complete the sine t for any t from 0 to 2 pi, of course, by using discrete points, but after we connect the points, then we can see t can be any real numbers from 0 to 2 pi. So it is a continuous curve. Although in the table, we only calculate the sine function at different values of t, but actually the sine t is defined for any t in this interval, right, from 0 to 2 pi. So therefore, we see a continuous curve. And because the 2 pi the number 2 pi is period of the sine function, then we can see the picture of sine on a larger interval. So if you here from 0 to pi, that's the picture we got earlier. I just use this to frame it so you can see that's the picture we got earlier. And then if you want to get picture from 2 pi to 4 pi, right? You just will get similar phenomena. So here's the sine, and then so you will get here. This is 3 pi and then 4 pi. So you get another period. So actually, we can extend this window I just framed. So just this is one period. So this one period, this picture will repeat if we look at the interval from negative 2 pi to 0. So that's another interval. So here is from negative 2 pi to 0. So we see the sine curve is defined for all real numbers t. Can be negative, can be positive, so all real numbers. So this sine of t has a domain. The function sine of t, its domain is all real numbers. So it is defined, the domain is entire real number set. That means t can be anything. There is a sine t defined. Yeah, sine t is defined for any t, which is a real number. But the function value is at most 1, at least a negative 1. So we notice that this sine function has the minimum value, negative 1, has a maximum value, positive 1. So that's the range of the function. So the range of the function is any value between negative 1 and 1. Yeah, so range, remember, range is all the possible values of this function. Yeah, it can be any value between negative 1 and 1, including negative 1, 1. Okay, so now you have the picture of the sine function, basic sine function. But the sine function, we can create a lot of variations. So understanding the picture of a basic sine function is very important. But before I end, I want you to highlight the 5 important points. That means if I want to produce just one period of the function, because I can extend this curve, the feature, to other intervals. So I want to create accurately one period, and with a reasonable amount of work. So we want to see what are the important points. So this is certainly a very important point, right? So this is the peak. That's another peak. And that's the x-intercept where the function value is 0. Okay, we have 3 intercepts. So let's see, this is a 0. When t is 0, the y is 0. When t is half of pi, this point, when t is half of pi, y is 1. When t is pi, y is 0, x-intercept. And then here, when t is 3 pi over 2, y is the function value. Yeah, we can say sine of t is -1. Yeah, when I said y means the function, not the y coordinate of that point anymore. So you see, usually we use y also to represent a function. So the notation can mean different things, right? So as long as in this certain context, you will be clear. Yeah. So here, the last point is 2 pi. When t is 2 pi, the sine t is 0 again. So you see, those are how many points? 5 points. Just to show the x-intercepts and also the maximum and minimum of the function values. So we call it 5-point method to do a sketch of one period of sine. And this technique can be applied to sketch a cosine curve, just one period of cosine curve. Once you have one period, and you can extend it to the entire domain. Yeah, the curve, if it's defined. But of course, we have to study where it is defined, right? Then we create one period, then we can extend it onto the entire domain of the function to get a whole picture.